On the first day of February 2003, the Space Shuttle Columbia, traveling at 18 times the speed of sound, broke apart over Texas and Louisiana at an altitude of about 60 kilometers. All 7 crew members died. The cause wasn't an engine failure, a navigation error, and not a software glitch. It was a hole the size of a dinner plate 30 years in the making, in the leading edge of the left wing, caused by a piece of insulating foam the size of a briefcase that had broken off the external fuel tank during launch, striking the wing at around 800 kilometers per hour, the most ordinary and avoidable part of this tragedy. The foam weighed less than a kilogram. The breach it created let superheated plasma into the wing structure during re-entry. The vehicle simply did not stand a chance and completely disintegrated in just minutes. That disaster didn't just kill 7 people. It exposed a fundamental truth about the space shuttle program that NASA had been quietly aware of for years. The heat shield was the single most dangerous, most expensive, and most maintenance-intensive part of the entire system, and no one had really figured out how to fix it. Now, 22 years later, 2 very different companies are making 2 very different bets on finally solving what Elon Musk himself once called a thorny issue. One is SpaceX, with a rocket that lands itself back on the pad and carries 18,000 ceramic tiles on its belly. The other is Sierra Space, with a vehicle that looks more like a miniature space shuttle than anything NASA has flown since Columbia's sister ships were retired in 2011. And the race between those 2 approaches, the brute force mass production strategy versus the precision aerospace strategy, is going to tell us a lot about which direction reusable spaceflight actually goes from here. The race to change the future, ladies and gentlemen, is well and truly on. But to understand why both of these solutions are so radical, you first need to understand just how badly the shuttle failed, because the numbers are genuinely shocking. The shuttle was supposed to fly like an airplane, that was the promise. Launch it, land it, turn it around in 2 weeks, fly it again. In practice, the thermal protection system, the ignored heat shield, made that vision almost laughable. The shuttle's belly was covered in 24,300 individual ceramic tiles, and here's the part that should stop you cold. Almost every single one of them was a different shape, different dimensions, different curvature, custom fitted to its exact location on the vehicle. If one got damaged, and they did constantly, you couldn't just grab a replacement off a shelf. You often had to manufacture a new one from scratch, at a cost of over $1,000 per tile before you even counted the labour. The tile work alone required roughly 2 full man-years of effort per flight, 2 years of human labour per mission just on the heat shield. How could they ever think that this was a good idea? And the tiles themselves were extraordinarily fragile, so brittle that they needed cushioning pads beneath them just to handle the vibration of the vehicle flexing during flight. Engineers were genuinely worried that losing a single tile in the wrong location could cascade into a total structural failure. That fear turned out to be prophetic, just not in the way they expected. Columbia wasn't lost because a tile broke off. It was lost because debris punched through reinforced carbon panels on the wing's leading edge, a different part of the thermal protection system, and nobody caught it in time. The shuttle's design made it nearly impossible to inspect the underside from orbit, something that could only be discovered after launching. After every flight, tiles had to be re-waterproofed, a 5-day process involving workers in full hazmat suits, because the chemicals involved were genuinely hazardous. The turnaround time that was supposed to be 2 weeks always stretched into months. In the later years of the program, it sometimes stretched to over a year. The shuttle flew 135 times over 30 years, and yet pushing on with a flawed shuttle seemingly wasn't deemed as mission critical. The average cost per launch? Around $1.5 billion. That's billion with a B. The heat shield wasn't the only reason for that number, but it was a main contributor. So that's the weight of the inheritance. That's the gigantic problem sitting on the table. When SpaceX and Sierra Space sit down at the dinner table and argue over the correct design of Starship and Dream Chaser. Same goal, same destination, same shared inspiration spawned from tragedy, but with completely different solutions. Let's start with Starship, because the philosophy is almost shocking in its simplicity. Simplicity that Sierra Space could only laugh at. Where Columbia obsessively attempted optimization with every tile custom fit and every contour precisely matched, SpaceX did almost the exact opposite. Starship's approximately 18,000 hexagonal tiles are, for the most part, deliberately uniform. Same shape, thickness, and geometry across the windward surface of the vehicle. That's not the most aerodynamically perfect solution. It does add some mass, but the engineering trade-off is enormous. You can mass produce them, and you can stockpile them. When a tile gets damaged, you pull it off and put an identical one in its place. No custom fabrication, no 6-week wait, no specialist artisan carefully shaping ceramic to fit a unique curve for 2 full years to repair. You treat it the way you'd treat a broken floor tile in your kitchen, except the floor tile is made of advanced ceramics and attached to a rocket. Laughably simple. The material itself is a derivative of the Shuttle era toughened silica ceramic system. But SpaceX modified the chemistry in ways that matter massively. The black glass coating on each tile, the layer that radiates heat away during re-entry, has had about 20% of its boron tetrasilicide replaced with molybdenum disilicide. That full mouthful change isn't something you'd notice by looking at it, but it significantly improves thermal shock resistance, which is critical because Starship goes from freezing cryogenic temperatures in orbit straight to searing hot plasma temperatures during re-entry almost instantaneously. The thermal gradient that creates, the rate at which the tile is forced to change temperature, is one of the main ways ceramic materials crack. Just ask anyone making an overpriced bespoke salad bowl. The modified chemistry to bolster the coating now handles that transition exponentially better. The internal fibre structure is also different from the Columbia. Starship tiles use larger diameter aluminum fibres instead of the Shuttle's silica fibres. While it does increase weight slightly and makes the tiles a bit more thermally conductive, which isn't ideal, but does without doubt dramatically make them more mechanically robust than its predecessor. They're harder to chip, harder to crack under impact, and more resistant to the kind of minor damage that would have grounded a previous shuttle for weeks while a replacement was fabricated. Then there's the backup system. This is the one improvement that might actually matter most. Beneath the primary ceramic tiles on Starship is a secondary ablative layer, a silicone-based felt material, designed to safely melt or vaporize away to protect the underlying surface. Basically, it's high-tech insurance. If a tile cracks, loosens, or gets knocked completely off the vehicle during re-entry, that ablative layer underneath can sacrificially erode, dissipating the incoming heat before it reaches the stainless steel hull. It buys time for the crew. It provides margin for decisions. The shuttle had no equivalent. Zero insurance, zero time, no such luxury to decide. If reinforced carbon-to-carbon failed on the shuttle, there was nothing behind it, just structure. Columbia demonstrated the true gravity of grim and total failure exactly. SpaceX also developed something called crunch wrap. And yes, that is the actual name they use internally, which is a gap-filling material designed to seal the spaces between tiles. The gaps between tiles were historically one of the most dangerous failure points on any tiled heat shield, because hot gas can intrude and attack the underlying structure. Crunch wrap was first tested on Ship 37 during Flight 10, and the results were telling. Sections protected by it showed near zero damage, while areas without it showed visible ablation. That's the kind of data point that engineers only dream about. The attachment system is another complete rethink. Every shuttle tile was bonded with a specialized adhesive that took 16 hours to cure and then had to be physically supported, often with a jack for another 16 hours while it set. Multiply that by thousands of tiles, and you can understand why turnaround times collapsed. Starship uses a mechanical system, each hexagonal tile mounted on a single metal stud, welded directly to the stainless steel hull. The flexible felt blanket sits between the hull and the tile for insulation and cushioning. The tile is then secured with a self-locking acorn nut. The whole system allows for slight movement as the hull expands and contracts through heating cycles, instead of fighting that expansion and cracking under the stress. It's modular, it's mechanical, and critically, it doesn't require a 16-hour wait between removing a damaged tile and installing a new one. And here's where Starship's architecture does something the shuttle physically couldn't. The shuttle was side-mounted, with the orbiter riding next to a foam-covered external tank during ascent, which meant it was directly in the path of any debris that might shed from that tank. Design killed Columbia. How could it stand a chance? Starship, on the other hand, is top-mounted on its super-heavy booster. There's no foam-covered tank sitting beside it, no debris pathway aimed directly at the heat shield during ascent. That single architectural difference removes an entire category of catastrophic failure mode and single-handedly saves lives. So that's Starship's answer. Dream Chasers is completely different. And honestly, the more interesting engineering story and more complicated. When Sierra Space unveiled this vehicle, the first reaction most people had was, that looks like a baby space shuttle. And that's not wrong. Dream Chaser is a lifting body spacecraft, which means it generates aerodynamic lift during re-entry and glides to a runway landing instead of splashing down in the ocean under parachutes. That design choice is what makes it unique among current commercial spacecraft. Dragon lands in water, Starliner lands in water, Dream Chaser lands on a runway like an airplane. For certain missions, particularly ones involving cargo that can't handle the G-forces and constant jostling of a splashdown, that matters enormously. But that design choice is also what makes the thermal protection system so much harder. A capsule hits the atmosphere like a baseball bat to a watermelon. It creates a shockwave in front that deflects most of the heat around the vehicle, and you just need to protect one face, the bottom, where it lands, very, very well. Dream Chaser's design philosophy is totally unique. It flies through the atmosphere, generating lift, changing angle of attack, with heat loads distributed across a complex, three-dimensional surface. Unlike its predecessors and peers, the nose cap, wing leading edges, belly and sides all see different temperatures at different times during re-entry. Designing a thermal protection system so advanced, so sophisticated, that it needs to handle all of those zones in a vehicle that's also thin enough and light enough to fly like an aircraft from planet Earth to outer space and land back on terra firma, believe it or not, is genuinely a hard problem to solve. Sierra Space's answer uses around 2,000 individual silica-based tiles on the belly of the current vehicle called Tenacity. These tiles are roughly 10 by 10 inches each, larger and fewer than Starship's 18,000, which on paper means simpler maintenance and fewer potential failure points. Each tile is bonded to the airframe with RTV silicone adhesive, which is more refined than the Shuttle-era adhesives, but still requires individual testing and certification. During testing at Kennedy Space Center, engineers discovered that the acoustic vibrations produced by the Vulcan rocket at launch, combined with the aerodynamic flexing of the lifting body structure during flight, required a more sophisticated bonding process than the original design called for. That discovery cost time, not because it was unfixable, but because aerospace doesn't allow you to fix things and move on. You test, fix, verify, document, test again, verify again, and then maybe you get to move on. For the hottest regions, the nose cap and wing leading edges, where temperatures during re-entry can exceed 1,650 degrees Celsius, more than 3,000 degrees Fahrenheit, Sierra Space uses a material called toughened uni-piece, fibrous reinforced oxidation-resistant composite. Glad I got that one right. The name is a mouthful, but the concept is important. It's a toughened silica ceramic system, specifically designed to be more impact resistant than the reinforced carbon-to-carbon that the shuttle used in those same locations. The old RCC worked, but it also had very limited impact tolerance, which is why a rogue briefcase-sized piece of foam managed to kill Columbia. The material on Dream Chaser's nose and leading edges is designed to have more margin against exactly that kind of impact event. Again, design that saves lives. For the second vehicle, called Reverence, Sierra Space is developing a proprietary silicon carbide ceramic and carbon fiber composite tile. Carbon fiber is one of the strongest structural materials we have by weight. The goal is to combine the extreme heat resistance of ceramics with the structural toughness of carbon fiber in a single material. In theory, these tiles can handle re-entry temperatures exceeding 1,740 degrees Celsius, significantly beyond what the shuttle's silica tiles could manage. That's not just an incremental improvement, that's breathing space. It means the material is operating well below its limits, under normal conditions all the time, which is exactly where you want to be if you're planning to fly the same vehicle 15 times or more. The tiles are only half the problem. What's powering Dream Chaser introduces a whole new layer of risk that almost nobody talks about. Most spacecraft use hypergolic propellants, chemicals that ignite spontaneously on contact, no ignition system required, reliable but also highly toxic and expensive to handle on the ground. Sierra Space went with a green propulsion system using high-test peroxide and kerosene. Better for ground crews, better for the environment, potentially cheaper to process between flights, but because it isn't the industry standard for orbital spacecraft, NASA required an enormous amount of new certification data. High-test peroxide is notoriously difficult to store. It can decompose if the storage system isn't designed with extreme precision, and a decomposing oxidizer in a spacecraft propellant tank is a very serious problem. Engineers spent years getting the storage system right. The VR3500 Vortex engine that burns this propellant went through multiple redesigns before it was considered flight-ready. So how do you make space wings fit inside a standard 5-meter rocket fairing to launch? Well, you just fold them. Easy, huh? Dream Chaser's wings tuck up during launch and deploy once the vehicle reaches space. That mechanism, the folding, the locking, the structural loads during landing, is an engineering marvel all on its own. And every kilogram of actuator and hinge hardware is a kilogram that can't be used for cargo. Sierra Space spent multiple design cycles trying to reduce that mass, while keeping the structure strong enough to handle the 1.5 G forces of a runway landing. Absolutely incredible. All of this is why Dream Chaser, which was originally planned to fly its first orbital mission in 2020, is now targeting late 2026 for a free flight demonstration that won't even dock with the ISS. That's a 6-year slip, but here's the thing. It would be easy to look at that number and conclude that the program is in trouble, but that assumption misses something important. The delays aren't coming from one catastrophic failure, they're coming from the accumulated weight of doing a genuinely challenging thing correctly. Are you ready for it? It's a spacecraft that behaves like an aircraft while flying at orbital speeds, with a green propulsion system that's never been certified for this application before. With folding wings, a tiled heat shield on a lifting body, that's not a capsule, with another heat shield bolted to the very bottom. Every subsystem is first of its kind, and NASA is not in the business of being casual about anything first of kind. The Shake and Bake campaign in late 2024, the acoustic and thermal vacuum testing at NASA's Neil Armstrong Test Facility, found exactly the kind of problems you want to find in a test chamber instead of in orbit. Acoustic testing revealed that several avionics components were vulnerable to the specific vibration profile of a Vulcan rocket launch. Internal mounting brackets had to be redesigned and shock absorbers added. Intense thermal vacuum testing, which cycled the vehicle between about -50 and +250 degrees Fahrenheit repeatedly over 5 weeks, found minor leaks in the thermal control loops, the plumbing that keeps electronics from overheating. Those leaks were fixed, the test campaign repeated, and none of it was catastrophic. Good times. Amongst natural design challenges, we can't ignore the regulatory and safety layer, which is its own universe entirely. After the Starliner investigation, NASA fundamentally changed how it oversees commercial crew and cargo programs. The agency found that with Boeing, there had been a mismatch in engineering transparency, critical telemetry, and other data wasn't being shared in ways that let NASA catch problems early. The response was stricter oversight across all commercial programs, including Dream Chaser. Every software patch, every flight control update, every guidance modification now goes through non-negotiable, deep independent audit. Full end-to-end hardware-in-the-loop simulations running the entire flight sequence, from launch through re-entry, complete with runway landing in one continuous test, are now required rather than optional. Dream Chaser's fully autonomous design means NASA is also requiring simulation of hundreds of edge case failure scenarios, unexpected thruster misfires, partial sensor failures, communication dropouts during critical phases. The vehicle has to demonstrate it can handle all of them before anyone gets near a launch pad. So how do you actually compare these two systems? Because at this point you might reasonably be wondering which approach is better, and maybe hoping you can combine the two and build your own rocket to launch. But the honest answer is that it depends entirely on what you're trying to do. Sorry, no rocket stealing today. Dream Chaser's 2,000 tiles versus Starship's 18,000 is a real advantage in simplicity and maintenance burden. Fewer components means fewer things to inspect, fewer failure points, fewer replacement cycles. Dream Chaser's tiles are also bonded directly to the airframe rather than mechanically attached, which in some ways is structurally simpler. No studs, no acorn nuts, no flex blankets. And for its intended mission profile, low Earth orbit cargo, relatively gentle re-entry energies, runway landing, 15+ flights, the thermal protection system doesn't need to be armoured like Starship's. But Starship is not flying to low Earth orbit. And coming home, it's flying to the moon and coming back. Eventually, it's flying to Mars and coming back. Which means re-entry velocities that make orbital return look like an afternoon in Grandpa's La-Z-Boy by comparison. The 18,000 tiles, the ablative backup layer, the crunch wrap gap sealing, the molybdenum-modified glass coating. All of that redundancy and complexity exists because the mission profile demands it. Starship is trying to be reusable more than 100 times under the most extreme re-entry conditions humans have ever attempted with a large crewed vehicle. The engineering reflects that ambition exactly. What both programs share is the recognition that the Shuttle's approach, extreme optimization, unique parts, labour-intensive maintenance, was actually the wrong answer. The Shuttle proved you could build a reusable spacecraft, and it also proved that reusable doesn't automatically mean affordable or operationally sustainable. The heat shield was the sole choke point. Both Starship and Dream Chaser, in completely different ways, are trying to redesign around it. Whether they've actually solved it won't be known until both vehicles have accumulated real flight history. Dream Chaser's first orbital flight in late 2026 will tell us an enormous amount about how well the tile, bonding and thermal protection systems hold up under actual re-entry conditions. Starship's ongoing flight test program is generating real data with every mission, and the improvements between flights have been genuinely rapid. The gap filling, the ablative backup layer, the mechanical attachment system, these aren't theoretical upgrades, they're tested changes with flight data behind them. What's actually remarkable about this moment is that if you step back from the technical details, two completely different engineering philosophies are being tested at the same time in the same era by teams that both fully understand a history that they absolutely don't want to repeat. The Shuttle was a warning. Both companies have read it carefully. The question both teams are asking now is which lesson turns out to be the right one. Is it over-engineered full armour, or is it precision and elegance? Columbia broke apart on a Saturday morning. Pieces of it landed across 3 states. Debris was found as far east as Louisiana and as far west as New Mexico. The crew had no warning, and there was nothing anyone on the ground could do. The investigation board that followed said that the physical cause was the foam strike, but the organisational cause was a culture that had become comfortable with known risks, comfortable with the fact that foam shed from the tank on almost every mission, comfortable with tiles getting damaged, comfortable with operating at the edge of what the system could survive, because it had survived so far. That's the real lesson from the Shuttle. Not just build better tiles, but build a system where tiles can fail without killing anyone, and where failure modes are discovered in testing rather than in operation at the highest stakes possible. Build margins, build redundancy, build something that doesn't require perfection to be safe. Both SpaceX and Sierra Space understand this fully, even if they've arrived at that understanding from totally different directions. The heat shield problem isn't fully solved yet, and may not be fully solved for years. But for the first time since the Shuttle flew, there are 2 vehicles in active development that approach it with clear eyes about what went wrong before, and genuine engineering, answers to the specific failure modes that caused it. That's not a small thing. That's true progress in aerospace. Slowly, expensively, and never quite completely, until suddenly one day it is solved.